Okay, so I'm going to do the example from last time. But I'm just going to make it a little cleaner.
You were on time.
Exactly.
Technically.
This is what I get for being on time.
I know, exactly.
Maybe I just be late all the time.
You've never seen the start of a class in your whole life. You were so close
I did
today.
just an hour ago. What are you talking about?
It was like a party in here.
Oh, I believe it.
Okay, so the pre-example from last time, coming up with it. So remember how I did this? I said like, okay, my principal stress is going to be 10, 0, 0, 0, negative 5, 0, 0, 0, 0. And then I just like not Wheel of Fortune, like what's Price is Right style. I just spun the coordinate system, you know. I gave it a good spin and just got random values. But I'm not going to give it quite as good a spin this time. I'm going to keep it a little cleaner. But I'm going to turn it into I'm going to go to a coordinate system where it's not a principal stress tensor. So I'm just going to go, so this time I'm going to rotate the coordinate system, let's say 30 degrees about z. And that's all I'm going to do, just one rotation. And what that's going to do is that's going to keep a 0 in this z spot. So we're just going to have a quadratic equation to deal with, and hopefully we won't have to simplify it as much. We can just plug values into stuff. So our rotation matrix is going to be cosine of 30, sine of 30, 0, negative sine of 30, cosine of 30, 0, 0, 0, 1. Um, 6.25, negative 6.5, 0, negative 6.5, negative 1.25, 0, 0, 0, 0. And this is in megapascals. And we want to find the eigenvalues. Those are the principal stresses. And the corresponding eigenvectors. Those are the principal coordinate axes. Okay, so the way we're going to do this is we're going to take 6.25 minus lambda, negative 6.5, 0, negative 6.5, then negative 1.25 minus lambda, 0, 0, 0, and this is just negative lambda, 0 minus lambda. And we're going to calculate the determinant. So that is 6.25 minus lambda times negative 1.25 minus lambda times negative lambda. And then minus a negative or plus 6.5 times negative 6.5 times negative lambda.
He says it's going to be quadratic.
Yeah, well, notice that both of them are multiplied by a lambda, so that'll be our zero root. So we can pull that stuff out, and we get so lambda times 6.25 minus lambda times the quantity negative 1.25 minus lambda I'll just keep going here. And then plus 6.5 squared, 42.25 is equal to 0.
Would it have to be negative lambda?
Yes. So this should be, I already, I think, accounted for it.
Or I guess maybe you could just multiply the whole thing by -1 and it doesn't matter, right?
That's true. I think I messed up the negative in both of these, so it works out fine. So yeah, that should be negative, but either way, one of our roots is, okay, so any any cubic has 3 roots. One of ours is 0. And so the other two come from, so I just have to FOIL this out, 6.25 times negative 1.25. So we have negative 7.81 minus 6.25 lambda plus 1.25 lambda plus lambda squared plus 42.25 is equal to 0. And so we have lambda squared minus 5 lambda plus 34.44 is equal to 0. And okay, yes. Okay, so I hate it when I'm trying to show how something works and then I mess it all up and then everyone's just like, it's impossible. That's like the take-home message. All I know is this is impossible. But okay, right. We did it right the whole time and then we did the quadratic formula wrong.
But
That's the synopsis of my calculus class, right?
but I'm just looking at that the equation one line up. Like if you were to factor that like the algebra way.
Yeah.
Like your coefficients. Oh wait. Yeah, that would be your thing, but then your zeros would be the opposite
Right.
of that.
Right.
Yeah. So
Okay.
yeah, you're right.
Okay. Okay, that was a lot of time wasted, but
Oh my god.
yeah. Well,
Team building.
but we got to the bottom of it, so that
probably would have helped to write out the factors, I think.
yeah. Okay, so the roots are
Jeez.
0, -5, +10. Okay, so now we are going to figure out the eigenvector that corresponds to each one of those. Okay? Okay, so first I'll start with lambda equal 0. And I'm going to go back to this equation. And I'm just going to plug in 0 for lambda. So we have 6.25 minus, I'll write it like this first, minus 0, negative 6.50, 0, negative 6.50, negative 1.25 minus 0, 0, 0, 0, and then this is, 0 minus 0. And we're going to say that this times our unit vector is equal to zeros, and we're just going to solve for that unit vector. Okay, so this says, so 6.25, negative 6.5, 0, negative 6.5, negative 1.25, 0, 0, 0, 0, times nx, ny, and z is equal to zeros. So this gives us three equations. The first one says 6.25 nx minus 6.50 ny is equal to 0. The second one says negative 6.50 nx minus 1.25 and y is equal to 0. And the third one doesn't help at all.
0 equals 0.
Yeah, it's correct, so
Yeah,
that's good.
Because we don't see nz, we assume that that one is our 0 root. Or that one's the 0 of our 3 roots. Or how does this work? I don't understand.
How did
Well, it's like, I think the z component of that eigenvector.
so
Yeah.
so for each one we're taking the root that we're we're going to do the roots one at a time, and we're just starting with 0, and we're plugging that in for lambda in the equation.
Well, yeah.
And then we're just finding values that work for these. There's no information about z, so we're just going to have to.
Well, that's what I mean. Because there's no information about z, would
Yeah.
not just assume it's 0?
We can't assume that. But hopefully what this is going to tell us is that, so is it possible that both of these two things would be true? So let's say, so is there any solution for this pair of equations besides nx and ny is equal to 0? Okay. So the first one says nx is equal to 6.5 divided by 6.25. So nx is equal to 1.04 ny. And now do it again for the second one. It says nx is equal to negative 0.192 ny. Okay. So the only solutions to this is nx equals ny equals 0. Okay, so what's a unit vector where nx and ny are equal to 0?
And z or k.
So right, or its opposite. So the unit vector satisfying this is 0, 0, 1 or 0, 0, -1. Okay, so that is the coordinate axis corresponding to our root of 0 is one of these two directions parallel to z.
And what's your eigenvector?
That's the eigenvector, yep. And so now we'll go on to the next root. So let's go to lambda is equal to -5. And so this time we have 6.25 minus -5, -6.50, 0, -6.50, -1.25 minus -5, 0, and then 0, 0, minus -5. And so that says 11.25, -6.50, 0, -6.50, what's that? Positive 3.75. Now I'm paranoid about doing any math in my head.
I agree with you.
Okay. 0, 0, that you're paranoid, or that I'm paranoid?
I agree with you that minus 1.25 minus -5 is positive.
Okay.
3.75.
And
I
then,
can't speak to your paranoia.
yeah. And so we have 11.25 nx minus 6.5 ny is equal to 0. And then negative 6.50 nx plus 3.75 ny is equal to 0. And then 5 nz is equal to 0. Okay, so right away we can see that nz is 0 for this one. That has to be the case because these have to be mutually perpendicular.
Is that true specifically just because of the nature of what we're doing here?
Yeah, I think
I can because they don't have to be like in general.
if you have, what is the requirement? If you are taking the eigenvectors of a symmetric matrix, I think you always get real eigenvalues and orthogonal eigenvectors.
Okay, that totally makes sense.
And if we do this, so always we're going to go 6.5 divided by 11.25 is 0.577. So these two are the same equation. And they say that nx is equal to 0.577, let's say 578 ny. So we can write this vector as, we can think of this as set ny equal to 1, okay? And that says that nx is this, but that's not a unit vector yet. And so now I'll take a unit vector in that direction. You can use the function unit v on a lot of your calculators. And you get 0.5, 0.8660, which is very recognizable as a 30-degree rotation of the principal stress tensor. And you know, where we saw that 30 degrees was that was how I made this stress tensor in the first place. I rotated 30 degrees. Okay, and then what about the other one? Well, you can always just use the cross product to get the third one, you know, or you could go through all this again, but it's sort of time consuming. But you know the third one is going to be perpendicular to the other two. So you just have to, whatever order you want your eigenvalues in, you just have to choose the third axis so that your new coordinate system satisfies the right-hand rule. Okay. So
is there like a way to easily do X and Y first?
well, yeah, whichever ones you do first and second can be your X and Y, and then just make the third one your third one. And then your, so the way I have it, so like, it has to satisfy the right-hand rule, but so let's say we'll make our X position, we're calling that our 0, and that corresponds to an axis, let's say 0, 0, 1. And then our second one was -5, and that will make that correspond to, you know, these can always be plus or minus, but we'll make that 0.5, 0.866, 0. And then our z is our 10. And to get that, we're just going to go x cross y. So now here's how you would do this. But that's how eigenvalues and eigenvectors work. So that I just wanted to show you that once, and then it got sort of messy. But you're going to go eigen VL, or if you have an 84, you're going to go to Wolfram Alpha and do this. But I'm going to go eigen VL. I'm going to put in that starting matrix, which was, where's that thing? This thing. So 6 point, -6.25, -6.50, -6.5, -1.25, 0. Good luck on your test.
Thank you.
And then 0, 0, 0. And that gives yay.
And then so when it gives you on the Inspire, will the order of the eigenvalues that it gives you correspond to the x, y, and
Exactly.
z on the vectors?
Yes, exactly. So and every solver will do that. So they'll give you the eigenvalues in the same order that they give you the eigenvectors.
Like in the vertical columns of the.
They give it in different formats, so you'll just have to like look at an example on Wolfram Alpha or whatever you're using. But yeah. And so yeah, it gives me 10, -5, 0. And then if I do the same thing, but eigen VC, same matrix. It gives 0.866, 0.50, -0.5, 0.866, 0, 0, 0, 1. And the way you read that is this axis corresponds to the first one they gave you. This axis corresponds, let me do a different color. This axis corresponds to the second one they gave you. And this axis corresponds to the third one they gave you.
So there's nothing more we need to do with the eigenvectors other than just find them?
Right.
Okay.
And I just want you to get used to that because eigenvalues and eigenvectors are little by little going to be an important thing you need to understand. But in this class, we have no use for the eigenvectors, really. We only care about the eigenvalues. Okay, any questions about that? Okay, how much time do we have? Now, let's stop there. So that's the end of me talking about eigenvalues and eigenvectors, but now we're just going to get back into just when we need them, we'll just plug them into a calculator. Okay. All right, that's all.